Hey, welcome. This is part 5 of my pimidi project. So far we've looked at the hardware side of things, basically what you see highlighted in the yellow here, and now in this video I'm going to concentrate just on the Python and various software components that get added into the controller. So let's have a closer look at the software. Okay, first new library I want to make is this one called midiio, and basically it's a wrapper for all the other IO libraries, the pimidi, the SSD 1306, MCP 4725, and GPIO, and I'll invoke it as a class. Then I want to make a settings.json file just to hold settings for the pimidi. It'll be things like what the CV voltage range should be, whether I display notes when I'm playing MIDI, those sort of things. Then also on the pimidi board, I'm going to create web services. I'm thinking of using fastAPI for that. Before I've used things like Flask, but I think fastAPI might be better as it better supports async type operations. And they'll do things like talk to midiio as well as update the settings. Then the last piece of the puzzle for now will be I'll create an Angular application. I'm used to using Angular for these sort of projects, and it'll have all the user-facing functionality like setting up the settings, running a sequencer, maybe interfacing to ChatGPT so I can try doing music AI type stuff, and probably being able to run a voice library. And they'll call the web services that are on the pimidi actual controller. Okay, let's have a look at the midiio library. So I implemented this as a class called midiio as well. And basically, like it says here, it's a wrapper for all the IO functions and a bit of the MIDI functionality as well. You'll notice in here I have some of these try and excepts. Sometimes I want to test this out just on a plain vanilla Pi 02W without having all the DACs and things attached, and to make sure it doesn't fail when I'm starting it up, I put these try and attach for some of the imports because it won't find the I2C rail otherwise. So let's get into the class. The main class is called midiio. There's some setup here, and during initialization it's again sets up the devices, and then it does a setup process during the initialization of the class, and we can have a look at that a bit later. Then after that we have the main functions that midiio can perform. So I can do things like save the settings. So there is a settings library out there, or a file out there, so we'll have a look at that a bit later. Then there's the major functions, so basically note on, note off, and this is where I'm wrapping up a lot of the different underlying functionality. So as well as doing playing the MIDI note on and off, it'll see whether we should be playing a equivalent CV voltage at the same time to run a CV controlled synthesizer. So if the CV MIDI channel is the same as the channels that's being played at the moment, then I'll attempt to play put out CV voltages and triggers that are in sync with the MIDI note being played. And then the last one here, if we've got a setting to say, hey, let's also display the notes on the OLED on the front of the pimidi device, then it's got a function here to show the MIDI note being played as well. Same thing for note off, but just turn everything off. Also have separate routines if we just want to manipulate the CV notes on and off as well, so could play those in parallel. And then finally this function in here, so I also wanted to make an async function for playing a note, and this is a little smarter than just the note on, note off. It'll do both operations with a delay in between, and it's kind of a fire this off and forget about it, so you can tell it to play a note for however long and it'll play the note and then turn it off at the end of the predefined time in the background without having to watch and manually turning off the note at the end. After that, we've got a whole bunch of getters and setters for getting and setting mainly the settings.json values, but also some internal settings that are just held at runtime. So those are the getters and the setters. we get into the actual main setup routine. This gets called when the class is first set up, and mainly its function is to set the parameters around getting the CV voltage in sync with what the MIDI notes will be. It does that by having a setting value for what the note coming out of the analog synthesizer would be at the lowest CV voltage out of the DAC, and also seeing what the voltage range is. It tells me how many octaves or semitones of notes the CV voltage can control, and then we can work out what's the first MIDI note that the CV voltage can play, and also what number of DAC values would be make up one semitone step, and that way we've got all the tuning information to keep if we're playing the CV as a synthesizer, keep that voice in sync with the MIDI voices as well. And then finally we've got some helper functions, so for things like displaying some text, it's just displays text in a certain part of the OLED display, so we can still show the IP address at the top half and show a changing MIDI note at the bottom. Things like getting a readable name for the MIDI note being played, and also a little helper function here to set the CV output value, and that's used during calibration. Okay, so that's the main sort of wrapper library, and let's just have a look at how calibration works. So I'm going to use this midiio CV calibrator routine to set the DAC voltage high and low to get the calibration values. So first I set the voltage high, and I see the DAC's outputting just over 5 volts. And then after 10 seconds, the calibrator is going to take it down to the lowest DAC value, and we see it's coming out at pretty much 0 volts. And we'll do the same thing with the frequency coming out of the synthesizer this time. So first we set it to a high voltage, and we see we're getting up near 4.3 kilohertz coming out of the synthesizer. I won't be using that anyway. But let's set it to the low voltage, and we see it's 130.4 hertz coming out, and that will set our low frequency calibration value. Let's have a look at the settings file. So this is a settings.json. We saw it being used by the midiio file. You can update them and read the settings there. So the settings I've got 3 settings to do with CV. So one is max volts. So this is used for calibration. So we need to know what's the maximum volts the DAC can put out. There's also minimum hertz. So again, for calibration, when the DAC is set to its minimum value, what's the frequency in hertz that the connected synthesizer will put out? This will give us the starting point for what notes the synthesizer can create. And then the third value is MIDI channel. So this tells what channel the CV will follow. So you can put it on the same MIDI channel as the MIDI output from the MIDI connector, in which case CV will just track with the actual MIDI output as well, but you can put it on a different channel and send separate MIDI to one MIDI output and to the CV. The other values in here are to do with the MIDI. So first one is the display option to show the current note being played on the OLED. You can either set that to true or false. And then the other one is the default channel used by the MIDI. So if you don't specify a MIDI channel when you play a note, then it'll use this default value for the channel, which in most cases you probably just want it to go out on one anyway. So I've also got a more full-featured test of the midiio that tests most things. So it's this program here, midiio test, and just in a nutshell what it's going through doing is it displays different settings by calling the getters and the setters. So first it displays sets the value to the same value, which will do a get and a set, and then it displays the value. That goes through fairly quickly. I do a save on the settings, which shouldn't really change them, and then we test out running the MIDI interface and the CV interface. First it tries running them so that they play the same notes, so no offset. I put this offset runtime parameter in here, so I can also set the offset so it's a certain number of semitones apart. So you'll see in the second run through here, it's going to be running the CV synth at 4 semitones higher than the Korg synth. Test turning the CV tracking off by basically setting it to a different MIDI channel from the main MIDI channel. Try running that again with no MIDI offset, and then the last test here is just a test of the synchronous function. So what you should see there is it'll call the synchronous function, it'll do this print display while the note's still playing, and then you'll see the note turn off in the background, even though it's the progress of the program's moved past there. I still just put in a wait for the task in here just to make sure this routine doesn't finish and the whole process doesn't finish before that note stops playing. So let's run the test. First we'll see the getters and setters. Now we see two synths being played in unison, and I'm showing the frequency of the Korg digital synth using MIDI and the CV synth at the same time. So you see the frequencies are fairly close on the two multimeters, which is a good sign. Also you can see the MIDI notes being displayed on the pimidi OLED. So now we see the same ascending series of notes, but this time I've got the analog synth or the CV voltage playing 4 semitones above what the Korg digital synth is playing. So I'm happy my calibration seems fairly close together. Now I'm just testing that I can play the MIDI notes and not have the CV track it by putting on a different MIDI channel. Now we're coming up to the async test. Keep an eye on the terminal. So we see the notes being displayed. It's already finished processing it, but the note keeps playing in the background until the duration finishes. So now let's have a look at the web services side of things. You see I've updated the diagram to show the uvicorn web server, and that talks to fastAPI and the web.py library to exposed web services. This is the web.py interface, and it connects to fastAPI. You can look up fastAPI on the web to find out more about it. I'm using that because it's seems to have good asynchronous functionality, which I'm going to use for some things. And it works a lot like Flask. Even the interface and the coding and the decorators look a lot like Flask, but in theory it's a bit more modern and should run a bit faster as well. Okay, so this is what the web.py does. So I'm importing the midiio interface and then making an object out of it. I'm calling O for object. And I'm also declaring the fastAPI interface here. Because this web.py gets started up to run the application when the pimidi Linux gets started up, I also use this to show the IP address of the of pimidi device now, so you can see that bit of code here, and I put it all in a big try except just to make sure it doesn't hold things up when it starts up. Down here we have all the web services that I've declared, and basically these are wrappers for all those midiio functions that I just showed you in the midiio library. So basically wrapping those, and the vast majority at the moment are just the getters and setters, and mainly for the settings. But you see here some of the functions, so I can do a MIDI note on and MIDI note off, call those functions here, so I can start playing the MIDI interface across the web. There's some utility functions here, things like this MIDI note reset. I found if I left I broke out of a program, it can leave notes playing, which can be annoying, so this one just clears all the MIDI notes no matter what they are. There's some other utilities like setting the CV value. There's utilities for setting the maximum volts, all those getters and setters. And one of the more interesting ones in here is why I'm ended up using fastAPI is, let's go find the async function. So there's an async function in here for playNote. So again, it's calling that async function I had down in midiio, and so I can call this from the web. And nice thing about it being asynchronous is I can send a request to the web service to play a note, and then the web server gets back to processing other events, and this can still turn off the note in the background based on what the duration is. And the final interesting thing in here is I'm also going to be using the fastAPI and uvicorn to publish my static website, which is an Angular website. So that's the thing that's going to be the user interface to all these web services. We'll see that in a sec, but the way I do that is this command here, app mount. So on the top level route, I declare where the static files are, and because it's on the top level route, just a simple backslash to retrieve the static website. I put it at the end of the file here, so it has to go at the end of the file, so it can fall through all these other more specific routes. If it doesn't find anything, but it finds a request for just the top level route, then it can publish the Angular app. So at the moment I just created a very basic Angular application called pimidi UI, and it's in my GitHub repository as well. The link's down below in the description. And really this is just to test out that I can build the application, then move the distribution files over to my static folder on the actual pimidi web server, and can see it come up. So let's first try building it, and I'm using Angular 17 now. So it's done the build, and the build is under the distribution folder, and if I look under browser I can see all the pieces that I need to move over to the pimidi web server to have this Angular application fire up. And just looking at the size, Angular 17 seems to be a lot smaller, the distributable, than what I was seeing under, I was last using Angular 14. Okay, I found the easiest way to get the files from the Angular project, and they're under the dist pimidi UI browser folder, over to my pimidi hardware, and to get them into the static folder over there is just to use this WinSCP utility. So I just grab the files that I want to move over, drag them over, and they're now on the Pi, and I can now see them in my pimidi project. And these are the static files that the fastAPI web interface will serve up when I just give it the default route. So finally, I want to test the web browser side of things. So I'm using the uvicorn as my web server and pointed at the web:app. I tell it to reload, so if I change the files, it'll reload the web interface, and I also tell it what host to use to publish the web on the pimidi device. So I can click on the link here, open pimidi, and there we see the Angular app being served up, and it's coming from those static files I just transferred over to the pimidi device. The nice thing about fastAPI, it has some utilities like this doc one, which allows you to see all the interfaces that are set up. It makes debugging easy. You can actually try the interfaces out using this this docs route, and makes the whole thing a lot easier to work with. Just a quick note here on setting up the pimidi. I've updated the service that the systemd runs to run the uvicorn service now. So this is the settings I had to use for the pimidi_uvicorn service, and that seems to run uvicorn okay, runs it out of my py directory and runs the correct web app. And the other thing I had to do was update the pimidi setup.sh. So this is the bash script that sets everything up, and if you follow this or just run it, it will also install the fastAPI, the uvicorn web server, and then install the updated systemd service for uvicorn. So that's about it for this video. I think we've got enough in there. Next video I'll be looking at the Angular pimidi UI, probably try and get the settings functionality completed in there. So I'm thinking of using a tab interface on that, and have settings, sequencer tab, an AI tab is what I want to play around with, and maybe also a library of settings that I can apply to a synthesizer. So that's all coming up, but first one will be just the settings tab in the next video.